Hi, this video accompanies the file I attached along with the lecture notes and is a completed version of the example we started in class. The file name is decisiontree.py. In this example, we learn how to import data from the built-in datasets in scikit-learn. Then we do some basic data manipulation to remove the unneeded features in classes in order to simplify the classification problem. Then we split the data into a training and test set as explained in the lecture notes. We use the training set to train the tree classifier and finally evaluate the accuracy of the tree classifier on the test data. Let's explore the code example together. Observe the various modules we import on lines 7 through 10. Read the specific comments I put here in order to see their exact purpose. The iris dataset we use here for the experimentation is built into the scikit-learn module. Line 7 imports it. Line 8 imports the NumPy module. The NumPy module has useful numerical functions and data structures such as NumPy arrays that are necessary for efficient processing and training of the models that are used in scikit-learn. OptParser will be used to look at the command line arguments provided by the user in order to permit a verbose mode that is going to output more detailed information. The more detailed information is useful for learning about the details in the example. Finally, we import the tree classifier model from the scikit-learn module. On lines 13 through 20, we use the OptParser, which was introduced in earlier lectures to allow students that want to see what's going on in detail to do so by running the program with the -v option, as I've indicated here. Let's go ahead and run the program with the -v option. The first thing we see is this notification that verbose mode has been activated. Then it waits for the user to press the Enter key in order to continue. In the next part, lines 23 through 35, we recap some of the functions that are specific to the NumPy module. We covered these in class, but let's review them here. On line 29, we show how we can create a NumPy array from an ordinary Python list. On line 31, we inspect the data type of the NumPy array we initialized on line 29 and named test. On line 32, we display the contents of the NumPy array named test. And on line 34, we demonstrate how to show the size of each dimension of the dataset using the shape property of the NumPy array. In this case, there's only one dimension with 3 elements. Pay attention later when we display the dimensionality of the iris dataset. Scrolling down a bit in our Python file, we see on lines 40 through 42 that we load the iris dataset and extract the input vector and the target vector using the data and target properties of the iris dataset, respectively. On line 44, if verbose mode is selected, we demonstrate how to access various properties that might be of interest and are not of particular use to accomplish the task at hand. That is not to say that they may be useful in another context. On line 51, we print out a long text description of the iris dataset. Let's see what that looks like when I press Enter to continue running our script. This is the long text description displayed here. We can scroll up and down to view it in its entirety. I'll leave that for you to read. Then, on lines 55 through 57, we use a for loop to display the name of each target class that correspond to the numerical labels in the target vector. In this data set, each is a variety of the iris flower: Setosa, versicolor, and virginica. Class 0 corresponds to Setosa, Class 1 corresponds to versicolor, and Class 2 corresponds to virginica. The loop on lines 60 through 61 prints out the column labels in the input vector. Notice we will only use the first two columns for the classification problem. Column 0 is the sepal length, column 1 is the sepal width, column 2 is the petal length, and column 3 is the petal width. Finally, we display the shape of the data set's input and target vectors. Notice that they each have the same number of rows. This is important. The number of rows must match. Scrolling down even further in our Python file, we see on lines 72 through 86, there's a discussion in these comments that concerns the array slicing operations we demonstrated in class. Array slicing operations can quickly get us results, but these techniques are more difficult to generalize to more complex tasks. You're welcome to revisit the array slicing tutorial at the provided link and copy and paste any of these commented lines into Python for testing. For now, we will leave that for your own exploration. On lines 88 through 134, so we're all going to try to get on the screen at once. We have code here that composes 4 vectors representing the training input and target vectors, as well as the test input and target vectors. The code also only uses the first 2 features in the input vectors, that is, columns 0 and 1, thereby eliminating columns 2 and 3. Class 0, which corresponds to the Setosa variety, is also eliminated from the training and testing sets by ignoring any records or rows where the target class is 0, indicating Setosa. This code does quite a bit and might be daunting to look at first. However, if you look closely, many of the lines are comments and others are related to providing verbose information to the user, rather than being functionally important for processing the data. Once you understand what's going on, you'll notice that there are perhaps only a dozen or so lines that are really important that do all of the important work. Lines 93 through 99 initialize the empty training and input target vectors, as well as the testing input and target vectors. These variable names use X to represent input and Y to represent targets as a shorthand to keep these variable names reasonably short. Notice that these are not yet NumPy arrays. We're working with basic Python lists at this point. Sometimes it's easier to work with ordinary Python lists and then convert to NumPy arrays in the last step. That's the approach we take here. This loop on line 102 visits every valid row index in the data and refers to the current index as I. On line 103 is a condition which eliminates class 0 or Setosa from the final training and testing vectors by checking to see whether the target value at the corresponding index is 0. which corresponds to the Setosa class. If it's something other than 0, then the statements on lines 107 through 128 are executed, and these lines add the data point to either the training or testing sets as appropriate. On line 111, we create a new row based on the original data's first and second columns at indices 0 and 1 respectively. On line 114, we decide whether to place the new row of data into the training or test sets. The logic inside of this if condition will be only true when dividing the current index by 5 will have a remainder of 0. This means that the condition will be true for every fifth element, or row. The code that is then executed on lines 115 through 121 adds the data point to the testing set, resulting in 20% of the data being reserved for testing. Otherwise, the remaining 80% of the data is added to the training set on lines 123 through 128. Finally, on lines 131 through 134, each of the data sets is converted to a NumPy array for later processing. Let's see the code on lines 102 through 134 run by pressing enter in the script. So at this point, we've executed all the way up to lines 134. Let's scroll down a little bit to see the rest of the program. On lines 141 through 150, we train the model, which we see is a relatively simple process now that we have the data in the form that we need it. On line 141, we set a variable to remember the maximum depth that we want to permit in our decision tree. On line 145, we instantiate an untrained or empty decision tree model with the indicated maximum depth. On line 146, commented out shows how we would create a new decision tree classifier model with the default metaparameters. On line 150, we fit the model to the data by passing the training input feature vector and the target vector to the model's fit function. In the last part of our program, on lines 153 all the way to the end at 186, we evaluate the performance of the model. That is, we measure its accuracy of making predictions against the test set. Lines 158 and 159 initialize the number of correct and incorrect model predictions. On line 161, we pass the test feature vector to the model's predict method and receive an array or list of predictions in return. The for loop on lines 167 through 177 compares each model prediction with the known label in the test target vector and counts the response as being correct or incorrect as appropriate. Line 182 computes the accuracy, and line 183 displays it. Let's run through the rest of the program by pressing enter. We see in this example that the number of correct predictions against the test set was 17, and the number of incorrect predictions was 3, giving an overall accuracy of 85%. Your textbook talks about creating a data science laboratory environment complete with tools, models, and data for experimentation. The code presented here will serve as a foundation for such a data science laboratory environment that you will develop through your assignment number 2. Thanks for tuning in.